Everything you think you know about reality might be an illusion. The solid world around you? Not so solid. Time, the steady ticking force we rely on? It's not as constant as you think. And objects, physical things, can be in two places at once, as if reality itself can't decide where they belong. Even stranger, the simple act of observing something changes what it is. This isn't science fiction. This is quantum physics, the most mind-bending, reality-shattering branch of science ever discovered. And the weirdest part? Scientists never saw it coming. For centuries, we believed in a predictable universe governed by logic, order, and unbreakable rules. If you drop an apple, it will fall. If you light a fire, it will burn. Every effect has a clear cause. This was the world of classical physics, a place where everything made sense. But then, the universe cracked open. As scientists looked closer, down to the smallest scales of existence, they found something impossible. Atoms, the very building blocks of everything, weren't tiny, solid marbles like we once imagined. Instead, they were something stranger, flickering clouds of probability, existing everywhere and nowhere at once. Experiments revealed particles that could be in two places at the same time. Objects that seemed to communicate faster than the speed of light. Time itself behaves differently depending on how fast you move or how close you are to a massive object. And, perhaps the most disturbing discovery of all, reality changes just because we're watching it. Think about that. The universe behaves differently when we're looking, as if it knows. None of this should be possible. And yet experiment after experiment confirmed the bizarre, paradoxical nature of the quantum world. It defied logic, mocked our common sense, and rewrote the very foundation of physics. Einstein himself called it spooky action at a distance. Richard Feynman, one of the greatest physicists of all time, famously said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." So, how did we go from believing in a predictable clockwork universe to a reality where particles teleport, time bends, and the act of looking changes the world? The story of quantum physics isn't just about science, it's about shattering everything we thought we knew. And it all started with a few experiments that turned reality upside down. For most of human history, we believed the universe was like a perfect clockwork machine, precise, predictable, and governed by absolute laws. The motions of the planets, the forces of nature, and even the physics of everyday life seemed to follow clear, unbreakable rules. Isaac Newton's laws of motion and gravity had explained everything from falling apples to planetary orbits with astonishing accuracy. Science appeared to be on a steady path toward uncovering a complete and final understanding of the universe. But in the early 20th century, that certainty crumbled. A series of strange and unexpected discoveries shattered the very foundations of classical physics. Scientists uncovered a hidden world, one where particles could exist in multiple places at once, where matter behaved like waves, and where the mere act of observation could change reality itself. It was a revolution unlike any other in the history of science, one that defied common sense and rewrote the fundamental principles of how nature operates. This was the birth of quantum mechanics. At first, these bizarre findings weren't part of any grand theory. They started as tiny cracks in the classical worldview, odd experimental results that didn't fit into existing frameworks. One of the earliest puzzles came from the study of light. For centuries, scientists had debated its true nature. Was it made of particles, as Isaac Newton had proposed, or was it a wave, as Thomas Young's double-slit experiment in the early 19th century suggested? The question seemed settled in favor of waves, until something strange happened at the dawn of the 20th century. In 1900, German physicist Max Planck was studying a problem that seemed purely technical: how objects emit heat and light. Classical physics predicted that hot objects should release an infinite amount of energy at high frequencies, leading to a paradox known as the ultraviolet catastrophe. But this didn't happen in reality. To solve this mystery, Planck introduced a radical idea. Energy could only be emitted in tiny, discrete packets, which he called quanta. He didn't fully understand the implications of this idea at the time, but it marked the first step into the quantum world. Then came Albert Einstein, who took Planck's idea even further. In 1905, Einstein explained the photoelectric effect, an experiment showing that light could knock electrons off a metal surface. Classical wave theory couldn't explain why light below a certain frequency had no effect, no matter how intense it was. Einstein proposed that light wasn't just a wave, it was also made of individual particles, or photons, each carrying a specific amount of energy. This was a groundbreaking revelation. Light had a dual nature, behaving both as a wave and a particle. The old debate over the nature of light wasn't just unresolved, it was turned upside down. Einstein's work on the photoelectric effect would later win him the Nobel Prize and lay the foundation for quantum mechanics. As the years passed, more scientists stumbled upon quantum mysteries that defied intuition. Danish physicist Niels Bohr introduced a revolutionary model of the atom in 1913. According to classical physics, electrons should spiral into the nucleus due to electromagnetic attraction. But atoms were stable. Why? Bohr proposed that electrons could only occupy specific orbits, jumping between them in discrete energy levels. They couldn't move smoothly between these orbits. They could only quantum leap from one to another, emitting or absorbing energy in fixed amounts. It was an entirely new way of thinking about matter at the atomic scale. Yet the true strangeness of the quantum world emerged in the 1920s with the work of Werner Heisenberg and Erwin Schrödinger. Heisenberg formulated the uncertainty principle, which stated that it was impossible to precisely know both the position and momentum of a particle at the same time. The more accurately you measured one, the fuzzier the other became. This wasn't a limitation of technology, it was a fundamental property of nature itself. Schrödinger, on the other hand, developed the famous wave equation, describing particles not as solid objects but as waves of probability existing in a superposition of states until measured. One of the most perplexing discoveries came from the famous double-slit experiment. When electrons were fired through two slits, they formed an interference pattern, as if they were waves passing through both slits at the same time. But when scientists tried to observe which slit the electron passed through, the interference pattern disappeared. The electrons behaved as particles, choosing one path or the other. The mere act of measurement changed their behavior. This baffling result suggested that reality at the quantum level wasn't fixed until observed, raising deep philosophical questions about the role of the observer in shaping the universe. As quantum mechanics developed, even stranger phenomena emerged. Particles that could teleport across space, a concept known as quantum tunneling. Quantum entanglement, where two particles could be instantaneously connected regardless of distance, and time dilation effects that defied common intuition. These discoveries weren't just theoretical curiosities, they had real-world applications, leading to technologies like lasers, semiconductors, and quantum computers. Quantum mechanics wasn't just a new set of equations. It was a fundamental shift in how we understood reality. It challenged the deterministic universe of Newton and replaced it with a world of probabilities, uncertainties, and paradoxes. The quest to understand quantum physics has led to some of the most groundbreaking discoveries in history, but it has also left us with profound mysteries, still unsolved. What does it truly mean for a particle to exist in multiple states? Can we ever unify quantum mechanics with Einstein's theory of relativity? And does reality even exist independent of observation? These questions continue to puzzle scientists to this day. But to truly grasp how we arrived at this strange and mind-bending understanding of reality, we need to go back to the very beginning. Let's unravel the fascinating history of quantum physics and explore how a series of unexpected discoveries changed our world forever. Before quantum physics, scientists believed the universe operated like a finely tuned machine, obeying clear and predictable rules. This was the world of classical physics, a realm where objects moved in precise ways, forces acted in predictable patterns, and everything from the orbits of planets to the motion of falling apples followed logical laws. The theories of Isaac Newton and later refinements by scientists like James Clerk Maxwell and Pierre-Simon Laplace painted a picture of a deterministic universe, one where, if you knew the position and velocity of every particle, you could predict the future with absolute certainty. For centuries, this view of reality worked exceptionally well. It explained how the Earth orbits the Sun, how steam engines function, and even how sound waves travel through the air. It was the foundation of engineering, astronomy, and everyday physics. The world seemed like a vast clockwork system, governed by mathematical principles that left little room for uncertainty. Scientists believed they had uncovered the fundamental truths of nature, and yet, beneath the surface, cracks were beginning to form. One of the first challenges came from an unexpected place: light. Scientists had long debated whether light was a wave or a particle. Isaac Newton believed it was made of tiny particles, while others, like Thomas Young, showed that light could behave like a wave, creating interference patterns when passed through slits. By the 19th century, the wave theory of light was widely accepted, especially after Maxwell's equations elegantly described how electromagnetic waves traveled through space. The debate seemed settled. Light was a wave. Then came a problem that refused to be ignored. When scientists studied how heated objects emitted light, like the red glow of hot metal or the bright colors of a flame, they ran into something deeply puzzling. Classical physics predicted that objects should radiate energy in a way that led to an absurd conclusion. They should emit infinite amounts of ultraviolet and even X-ray energy as they got hotter. But this wasn't observed in reality. Instead, objects emitted light in specific, finite ways. This discrepancy became known as the ultraviolet catastrophe, and it signaled that something was seriously wrong with classical physics. At the same time, another mystery was unfolding. In 1900, a German physicist named Max Planck was investigating how objects emit and absorb radiation. In an act of desperation, he proposed something radical. What if energy wasn't continuous like a flowing river, but instead came in tiny, discrete packets? He called these packets quanta. It was a revolutionary idea, but at the time, Planck himself considered it merely a mathematical trick, not a fundamental change to physics. Little did he know, this simple assumption would shatter everything scientists thought they understood about reality. Another strange discovery soon followed. When light shined onto a metal surface, it sometimes ejected electrons in a phenomenon known as the photoelectric effect. Classical physics predicted that increasing the intensity of light should gradually increase the energy of the ejected electrons. But experiments showed something baffling. The intensity of light didn't matter as much as its frequency. Only light of a certain frequency, like ultraviolet, could knock electrons free, regardless of how bright the light was. This made no sense under classical physics. But Albert Einstein had an idea. In 1905, Einstein proposed that light wasn't just a wave, it was also made of individual particles of energy, which we now call photons. These photons carried energy in discrete amounts, and only those with enough energy could knock electrons loose. This idea built on Planck's quantum hypothesis and explained the photoelectric effect perfectly. For this, Einstein later won the Nobel Prize, but more importantly, his work added to the growing evidence that the universe didn't work the way classical physics had predicted. With each new discovery, the cracks in classical physics widened. A young Danish physicist named Niels Bohr took these ideas even further. Scientists had been struggling to understand the structure of the atom, and classical models failed to explain why electrons didn't simply spiral into the nucleus and collapse the atom entirely. Bohr proposed that electrons could only occupy specific energy levels and could jump between them by absorbing or emitting discrete packets of energy. His model worked astonishingly well in explaining the behavior of hydrogen atoms, but it introduced yet another strange idea. Electrons didn't move in smooth, predictable paths like planets around the sun. Instead, their behavior was dictated by probabilities. As the 20th century progressed, experiment after experiment confirmed that the subatomic world didn't follow the neat, orderly rules of classical physics. Reality was not deterministic in the way Newton had imagined. Instead, particles behaved unpredictably, sometimes acting like waves, sometimes like particles, and sometimes seeming to be in multiple places at once. The more scientists looked, the stranger things became. This was the problem at the heart of physics. The old, reliable laws that had explained everything for centuries were breaking down. The world was not as predictable as once thought. Beneath the surface of our seemingly solid reality, an entirely new set of rules governing the fundamental nature of existence. The discoveries of Planck, Einstein, and Bohr were just the beginning of a revolution that would redefine our understanding of space, time, and reality itself. Scientists were no longer just uncovering new facts. They were being forced to question the very nature of reality. How could something be both a wave and a particle? How could particles exist in multiple states at once? Why did physics behave differently at the smallest scales? These questions didn't just challenge old ideas, they demanded an entirely new way of thinking. The universe, it turned out, was far stranger than anyone had ever imagined. And solving these mysteries would require a bold leap into the unknown, a journey into the mind-bending world of quantum physics. The light bulb that changed everything. It all started with a simple but profound observation. When you heat a metal, it glows. A blacksmith working at a forge, a potter firing up a kiln, or even a piece of iron left too long in a fire, each of these glows with an eerie radiance. But why does this happen? And more importantly, why does the color change as the temperature rises? Scientists had long noticed that as objects got hotter, they didn't just glow brighter, they shifted in color. A piece of iron might start with a dull red glow, then turn orange, then yellow, and eventually, if hot enough, become white. Classical physics had a neat explanation, or so it seemed. The prevailing theory suggested that as an object absorbed energy, it should be able to emit any frequency of light. The more heat applied, the higher the frequency of light it should emit. If the theory were correct, this meant that at sufficiently high temperatures, objects should start glowing blue, then violet, and eventually even into the ultraviolet range. Theoretically, if you kept heating an object, it should release an infinite amount of ultraviolet light. An absurd prediction that clearly wasn't true. This strange inconsistency came to be known as the ultraviolet catastrophe. Scientists had hit a wall. Something about their understanding of light and heat was fundamentally flawed, and they needed a new way of thinking to solve it. Enter Max Planck. In the year 1900, Max Planck, a German physicist, was working on this very problem. He wasn't trying to revolutionize physics, he was simply trying to make sense of the data. And to do that, he proposed something radical. What if energy wasn't continuous? What if instead of being like a flowing stream, energy came in tiny, indivisible packets? He called these packets quanta. It was a bold idea. Planck wasn't suggesting that energy behaved like this in all cases, only when it was emitted or absorbed by atoms. And yet, despite his reluctance, his theory worked. When he assumed that energy was quantized, the ultraviolet catastrophe disappeared. The math lined up with the experimental data perfectly. But this simple fix opened an even bigger mystery. If energy came in discrete packets, did that mean light itself was made of particles? This was a direct contradiction to everything physics had previously assumed. For centuries, scientists believed light was a wave. It could bend, diffract, and interfere with itself. So, if light was really a wave, how could it also behave like a particle? This wasn't just an abstract puzzle. The very nature of reality was at stake. Planck had unknowingly cracked open the door to a new world, one that would soon be explored by some of the greatest minds in history. One of those minds was Albert Einstein. At the time, Einstein was a young and largely unknown physicist working at a patent office. But he was deeply fascinated by light and had been thinking about an unsolved problem of his own, the photoelectric effect. Scientists had noticed that when ultraviolet light shined on a metal surface, it could knock electrons loose. But there was a catch. According to classical physics, if light were just a wave, increasing the intensity should knock more electrons loose, regardless of frequency. Yet, in reality, only light above a certain frequency could dislodge electrons, no matter how bright the beam was. Einstein's insight was profound. He proposed that light itself came in packets, just as Planck had suggested for energy. These packets, which we now call photons, carried a fixed amount of energy determined by their frequency. A low-frequency photon didn't have enough energy to knock an electron free, no matter how many of them hit the surface. But a high-frequency photon, like ultraviolet light, had enough punch to do the job. This was groundbreaking. With this, Einstein not only explained the photoelectric effect, but also provided the first real evidence that light wasn't just a wave, it also behaved like a particle. For this revolutionary idea, he won the Nobel Prize in 1921. But more importantly, his work paved the way for a new field of physics, quantum mechanics. Planck and Einstein had shown that energy and light behaved in ways no one had expected. But what about matter? Could the same rules apply? Enter Niels Bohr. Bohr was grappling with a different puzzle, the structure of the atom. Scientists had known for some time that atoms contained electrons, but they didn't understand how they were arranged. The prevailing model suggested that electrons orbited the nucleus like planets around the sun. But this created a serious problem. According to classical physics, an orbiting electron should continuously lose energy and spiral into the nucleus, meaning atoms should collapse in a fraction of a second. Clearly, that wasn't happening. Bohr took inspiration from Planck's quantum ideas and proposed something radical. What if electrons could only occupy specific energy levels, or orbits, around the nucleus? And what if they could only jump between these levels by absorbing or emitting quanta of energy? This was a radical departure from classical physics, but it explained the stability of atoms perfectly. Electrons weren't gradually losing energy. They could only exist in defined states. When they jumped from one state to another, they absorbed or emitted light in specific, quantized amounts. Bohr's model worked beautifully to explain the spectral lines of hydrogen, the unique fingerprint of light emitted by hydrogen atoms. His ideas laid the foundation for the quantum revolution, but the rabbit hole went deeper. If energy was quantized, if light behaved like particles, if electrons existed in discrete states, what did this mean for reality itself? The answers would come from a new generation of physicists, including Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. They discovered that, at a fundamental level, particles didn't behave like tiny billiard balls, but instead followed strange and probabilistic rules. Heisenberg formulated the uncertainty principle, which stated that you could never know both the exact position and momentum of a particle at the same time. Schrödinger introduced wave functions, suggesting that particles could exist in multiple states simultaneously until observed. And Dirac's equations predicted the existence of antimatter, something that would later be confirmed in experiments. Quantum mechanics had rewritten the rules of the universe. What started as a simple question, why do hot objects glow, had led to a complete upheaval of our understanding of reality. Today, quantum mechanics is at the heart of modern physics, driving advancements in everything from semiconductors to quantum computers. And to think, it all began with a glowing piece of metal and a paradox that classical physics couldn't explain. The light bulb that changed everything wasn't just a metaphor. It was a literal shift in how we see the universe, proving that sometimes the smallest questions lead to the biggest revolutions. Einstein breaks reality. At the dawn of the 20th century, the world of physics was in turmoil. Scientists had spent centuries refining classical mechanics, believing that Newton's laws could explain everything from the motion of the planets to the behavior of everyday objects. But there were cracks in this foundation, mysteries that classical physics couldn't solve. One of the biggest involved light. Was it a wave or a particle? This question had haunted scientists for centuries. Then, in 1905, Albert Einstein shattered the very fabric of reality. At the time, most physicists firmly believed that light was a wave. The idea had been supported by Thomas Young's famous double-slit experiment in 1801, which showed that light could interfere with itself, creating patterns that only waves should produce. This reinforced the notion that light behaved like ripples on a pond, spreading out in all directions. But despite the overwhelming evidence supporting the wave theory, certain experimental results refused to fit the picture. One of these unexplained phenomena was the photoelectric effect, a strange observation that had baffled scientists. When light was shined onto certain metals, it would eject electrons from the surface. This effect was first discovered by Heinrich Hertz in 1887, but no one could explain why it happened. According to classical wave theory, the intensity of the light, how bright it was, should determine how much energy the electrons received. A brighter light should knock out electrons more forcefully, regardless of its color. But experiments showed something bizarre. Dim blue light could eject electrons with more energy than bright red light. This made no sense under classical physics. It was as if light was obeying a completely different set of rules. Enter Albert Einstein. In 1905, in one of 4 groundbreaking papers he published that year, Einstein proposed a radical idea. What if light wasn't just a wave? What if it also behaved like a particle? Building on Max Planck's quantum hypothesis, Einstein suggested that light was made up of tiny, discrete packets of energy, what we now call photons. Unlike classical waves that spread energy smoothly, these photons carried energy in specific chunks, and the energy of each photon depended solely on the light's frequency or color. Blue light, which has a higher frequency than red light, would have more energetic photons. When a photon struck a metal surface, it would transfer its energy directly to an electron. If the photon had enough energy, it could knock the electron free. If not, no amount of additional light, no matter how bright, could do the job. This was revolutionary. Einstein's idea explained the photoelectric effect perfectly. It also meant that light wasn't just a wave, it had a dual nature. It could behave both as a wave and as a particle, depending on how it was observed. This shattered the classical understanding of physics and laid the groundwork for what would become quantum mechanics. At first, many physicists, including Max Planck himself, were skeptical. The idea of light behaving as particles seemed to contradict the well-established wave theory. Even Niels Bohr, who would later become one of quantum mechanics' greatest pioneers, was hesitant to accept Einstein's interpretation. But experimental evidence continued to support Einstein's theory. In 1914, Robert Millikan, initially hoping to disprove Einstein, conducted precise experiments that confirmed the predictions of the photon theory. The photoelectric effect could only be explained if light truly behaved as Einstein had described. Despite the resistance, the scientific community had no choice but to acknowledge the truth. Einstein had not only solved the mystery of the photoelectric effect, he had changed physics forever. His work on photons was so groundbreaking that in 1921 he was awarded the Nobel Prize in Physics. Ironically, despite his role in shaping quantum mechanics, Einstein remained deeply troubled by its implications. He famously resisted the idea that the universe was governed by probability, leading to his famous quote, "God does not play dice with the universe." But there was no stopping the quantum revolution. Einstein's work had opened a door that could never be closed. Physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger would soon build on his discoveries, developing a theory that would completely redefine our understanding of reality. Einstein had broken reality, and the world of physics would never be the same again. The atom gets weirder. At the turn of the 20th century, scientists believed they had a solid grasp of the atom. It was thought to be the fundamental, indivisible building block of nature, a tiny sphere of matter, perhaps resembling a miniature solar system, where electrons orbited a central nucleus like planets around the sun. It was a neat, intuitive picture, one that fit comfortably within the laws of classical physics. But reality had other plans. In 1911, a quiet but revolutionary experiment shattered this simple view. Ernest Rutherford, a physicist with a reputation for asking difficult questions, set up an experiment that should have confirmed the accepted atomic model. Instead, it revealed something far more bizarre. Rutherford and his team directed a beam of tiny, positively charged alpha particles at an ultra-thin sheet of gold foil. If the prevailing atomic model was correct, these particles should have passed straight through, or at most, been slightly deflected by the evenly distributed mass within the atoms. For the most part, that's exactly what happened. Most of the alpha particles zipped through as if the gold foil was barely there. But then came the surprise. Some particles bounced back at extreme angles, as if they had collided with something incredibly dense and immovable. It was an outcome so unexpected that Rutherford later admitted it was as if you had fired a 15-inch shell at a piece of tissue paper and it bounced back. This meant only one thing. The atom was not the uniform, indivisible sphere everyone had assumed. Instead, it was mostly empty space, with an incredibly dense, positively charged nucleus at its core. The discovery was shocking. The very structure of matter was not what we had thought. It was a tiny, almost ghostly framework, with vast spaces separating the minuscule particles within. But one major problem remained, a puzzle that gnawed at physicists. If the atom had a dense, positively charged nucleus and tiny, negatively charged electrons swirling around it, then why didn't the electrons spiral inward and collapse into the nucleus? According to classical physics, this should have happened. Charged particles moving in curved paths should continuously lose energy in the form of electromagnetic radiation. This loss of energy would cause the electron's orbit to shrink, sending it crashing into the nucleus almost instantly. And yet, atoms didn't collapse. They were stable. The very existence of the world depended on this mystery. Why did atoms defy the rules? The answer came from an unlikely source, a young Danish physicist named Niels Bohr. Bohr had an unshakable curiosity, a willingness to challenge existing ideas, and an appreciation for the strange, new discoveries emerging in physics. In 1913, he proposed a radical solution to the mystery. Bohr suggested that electrons did not move freely around the nucleus in a classical orbit. Instead, they could only exist in specific, fixed energy levels, what he called quantized orbits. Imagine climbing a ladder. You can stand on one rung or another, but you cannot hover between them. Electrons, according to Bohr, behaved the same way. They couldn't drift smoothly between energy levels. They could only jump from one level to another. And when they did, they either absorbed or emitted energy in precise amounts. Discrete packets called quanta. It was a bold idea, and it worked. Bohr's model successfully explained why atoms were stable. If electrons could only occupy certain energy levels, then they wouldn't gradually spiral inward. Instead, they would remain in their designated orbits unless given or deprived of the exact amount of energy needed to make the jump. The theory also explained why atoms emitted and absorbed light in specific, predictable wavelengths, an observation that had puzzled scientists for years. But this solution, as satisfying as it was, came with a troubling implication. If electrons could only exist in certain quantized states, it meant that the universe wasn't smooth and continuous, as classical physics had always assumed. Reality itself seemed to be made up of discrete jumps, abrupt shifts, and rigid probabilities rather than seamless flows. The comforting predictability of Newton's laws was starting to crack. As physicists absorbed Bohr's ideas, they quickly realized that something even stranger was lurking beneath the surface. Bohr's model worked beautifully for hydrogen, the simplest atom, but it struggled to explain more complex atoms. And when scientists tried to probe deeper into the nature of electrons, they discovered that these tiny particles didn't behave like solid objects at all. They flickered between states unpredictably, refused to follow definite paths, and seemed to exist in multiple places at once. The atom had become a riddle wrapped in a paradox. Bohr's neat energy levels were just the beginning. Something far more unsettling was waiting to be uncovered. The double-slit experiment. Reality falls apart. In the quiet corridors of early 20th century physics, a simple experiment sent shockwaves through science, unraveling reality itself. It started innocently enough, a beam of light, 2 tiny slits, and a screen. But what followed shattered everything we thought we knew about the universe. Back in the 1920s, physicists were trying to understand whether light was a wave or a particle. For centuries, scientists had debated this mystery, proposing different theories, running experiments, and arguing over the results. Then came the double-slit experiment, a test so simple, yet so baffling, it left even the greatest minds in physics staring in disbelief. The idea was straightforward. Scientists aimed a beam of light at a barrier with 2 narrow slits. On the other side was a screen that would show where the light landed. If light was made of tiny particles, like little bullets, it would go through one slit or the other and form 2 distinct lines on the screen. But if light was a wave, like ripples in a pond, it would spread out after passing through the slits, overlap, and create a pattern of alternating bright and dark bands on the screen, something known as an interference pattern. So they conducted the experiment. The light passed through the slits, and sure enough, an interference pattern appeared on the screen. It behaved exactly like a wave. That should have been the end of the story. Light, it seemed, was a wave. Case closed. But scientists, being the curious creatures they are, decided to take things a step further. What if they placed tiny detectors at the slits to see which path the light actually took? Did it go through the left slit, The right slit? Both? That's when everything fell apart. The moment they turned on the detectors to measure which slit the light went through, the interference pattern vanished. Instead of acting like a wave, the light behaved like tiny particles, forming two solid bands on the screen, exactly as if it had chosen one slit or the other. This was impossible. It was as if the light knew it was being watched. When it was unobserved, it acted like a wave. The moment it was measured, it collapsed into particles. The act of observation itself changed the outcome. Physicists were stunned. This wasn't just about light, electrons, atoms, even molecules. Everything they tested behaved the same way. Reality, it seemed, wasn't fixed, it was fluid. Particles existed in a state of limbo, occupying multiple possibilities at once, until something, a conscious observer perhaps, forced them to choose. This strange phenomenon became known as superposition, a core principle of quantum mechanics. It meant that at the quantum level, a particle wasn't in any one place, but rather in all possible places at once. Until someone looked, and the deeper scientists dug, the stranger it got. If particles could exist in multiple states until observed, what did that say about reality itself? Was the universe just a vast sea of possibilities, crystallizing into reality only when we paid attention to it? Even Einstein, the genius behind relativity, was deeply disturbed by these implications. He famously remarked, "I like to think the moon is there even when I'm not looking at it." To him, the idea that observation could determine reality was absurd. But no matter how hard physicists tried, they couldn't escape the experiment's eerie conclusion. And it didn't stop there. Later variations of the experiment revealed even more unsettling mysteries. Scientists found that even if they waited to decide whether to observe the particle after it had already passed through the slits, it still chose its behavior retroactively, as if the future could affect the past. This wasn't just science fiction. It was cold, hard reality. Some physicists began to wonder, what if consciousness itself plays a fundamental role in shaping reality? Could it be that the very act of thinking, of perceiving, was somehow linked to the physical world in ways we couldn't yet understand? The double-slit experiment forced scientists to confront a terrifying possibility, that reality isn't something solid and objective, but something fluid and undefined until observed. It suggested that, at the deepest level, the universe might not even exist in a definite state unless someone is there to witness it. Even today, nearly a century later, no one fully understands what the double-slit experiment truly means. It remains one of the greatest unsolved mysteries of physics, a doorway into the bizarre, mind-bending world of quantum mechanics. One thing is certain, the simple act of looking changes everything. Schrödinger's cat and the uncertainty principle. The year was 1927, and physics was in chaos. The world's brightest minds had been unraveling the mysteries of the atomic world, but what they found was unsettling. The deeper they looked, the stranger reality became. Among these discoveries was something called the uncertainty principle, introduced by Werner Heisenberg. It wasn't just another complicated equation or a minor technicality, it was a bombshell. It stated that the more precisely you measure a particle's position, the less you can know about its speed, and vice versa. In other words, no matter how advanced science became, there would always be things about the universe that were unknowable. This wasn't a flaw in our measuring tools or a problem that could be solved with better technology. It was a fundamental rule of nature. And for many physicists, this was deeply unsettling. One of them was Erwin Schrödinger. Schrödinger was no ordinary scientist. He was a man who had spent his life trying to make sense of the quantum world. But this new idea? He hated it. The idea that nature itself was unpredictable, that particles had no definite state until observed, was absurd to him. Physics had always been about certainty, about finding the rules that governed the universe. And yet Heisenberg was saying that the universe didn't follow the kind of rules people expected. Schrödinger wanted to prove just how ridiculous this idea was, and so he came up with one of the most famous thought experiments in history. Imagine a simple box. Inside it sits a cat, alive, well, and completely unaware that it has just become the subject of one of the greatest paradoxes in physics. Next to the cat is a radioactive atom, something so small that it behaves according to the strange laws of quantum mechanics. This atom has a 50% chance of decaying within a certain time. If it does, a tiny Geiger counter will detect it, triggering a mechanism that releases poison into the box, killing the cat. If the atom does not decay, the cat remains unharmed. From a logical perspective, it seems straightforward. Either the atom decays and the cat dies, or it doesn't and the cat lives. But in the quantum world, things don't work that way. According to the rules of quantum mechanics, before someone opens the box to check, the atom exists in a state of superposition, both decayed and not decayed at the same time. And since the cat's fate is tied to the atom, that means the cat, too, is in a bizarre state of being both alive and dead simultaneously. It is only when someone observes it, when the box is opened, that the cat's state is determined. This wasn't just some philosophical exercise, it was quantum mechanics in action. To Schrödinger, this whole idea was ridiculous. A cat couldn't be both alive and dead at the same time. The very suggestion was absurd. He thought this would prove how flawed quantum mechanics had become, how physicists had taken their ideas too far. Surely this paradox would force them to rethink everything. But the strangest thing happened. Rather than rejecting the idea, many physicists embraced it. They argued that Schrödinger's cat was not proof against quantum mechanics, but rather proof of just how strange and real the quantum world truly was. This wasn't just theoretical. It was a genuine consequence of how reality worked at the microscopic level. Over time, more experiments backed this up. Scientists began uncovering bizarre phenomena like particles being in two places at once and influencing each other across vast distances instantly, something Einstein himself called spooky action at a distance. Reality, it seemed, was not as simple as people once believed. For centuries, humans had thought of the universe as a clockwork machine, where everything followed predictable logical rules. But quantum mechanics shattered that idea. It revealed a world where uncertainty was not a mistake but a feature of existence, where particles didn't have definite properties until they were observed, where a cat could, in some sense, be both alive and dead at the same time. This wasn't easy to accept. Even Einstein, one of the greatest physicists of all time, refused to believe that the universe operated on pure chance. God does not play dice with the universe, he famously declared. But quantum mechanics didn't care what anyone believed. The experiments kept proving it right. Schrödinger's cat became more than just a thought experiment. It became a symbol of the strangeness of quantum mechanics. Scientists debated its meaning for decades. Some proposed alternative explanations, trying to make sense of how observation influenced reality. Others suggested that every possible outcome of an event actually happened, just in different parallel universes. This idea, known as the many worlds interpretation, suggested that in one universe, the cat was dead, while in another, it was alive. And every time a quantum event occurred, reality split into multiple timelines, each following a different outcome. If true, this meant that there were countless versions of reality, branching off every second, creating infinite possibilities. It was a mind-bending thought, one that turned science fiction into something terrifyingly real. And yet, despite all the debates, all the interpretations, one thing remained clear. The quantum world did not follow human intuition. It didn't care about common sense. It didn't care about what people thought was logical. It operated by its own rules. Rules that were stranger and more mysterious than anyone had ever imagined. Schrödinger, for all his skepticism, had helped shine a light on one of the greatest mysteries of the universe. His cat was more than just a hypothetical paradox. It was a glimpse into a reality far beyond human understanding. A reality where uncertainty was not just a limitation, but a fundamental truth. And so even today, the question remains, when the box is closed, is the cat alive, dead, or something else entirely? Quantum entanglement, the universe's strangest secret. If you thought quantum mechanics was already strange, wait until you hear about quantum entanglement. This is where things go from simply bizarre to downright mind-bending. Imagine taking two tiny particles, like electrons or photons, and somehow linking them together in such a way that their properties become forever intertwined. No matter how far apart they are, whether separated by a few inches or stretched across the entire universe, what happens to one instantly affects the other. There's no delay, no signal traveling between them. It just happens, as if they are still connected by some invisible thread that defies space and time. This concept baffled even Albert Einstein, who famously called it spooky action at a distance. To him, this idea was so absurd that he refused to accept it as reality. In his view, the universe should behave in a logical, predictable way, with clear rules about cause and effect. He was convinced that something was missing in the equations of quantum mechanics, some hidden variable that would eventually explain everything in a way that made sense. But reality had different plans. In 1964, physicist John Bell changed everything. He devised a groundbreaking mathematical theorem, now known as Bell's theorem, which set up a way to test whether quantum entanglement was real or just a misunderstanding of the laws of physics. His work led to a series of experiments that shattered the last hopes of those, like Einstein, who believed entanglement was just an illusion. The results were clear. Entanglement was real. There were no hidden variables, no secret communication between particles. The universe really does behave in this bizarre way, where two entangled particles can influence each other instantaneously, no matter how far apart they are. Since then, scientists have tested entanglement in countless experiments, and every time it has proven to be one of the most mysterious and undeniable aspects of quantum mechanics. In some of the most dramatic demonstrations, physicists have entangled particles and then sent them miles apart, sometimes even into space, only to find that when they measured one particle, the other reacted instantly. No signal could have traveled between them in time, especially not at the speed of light, which is supposed to be the ultimate speed limit in the universe. So, what's actually happening here? How can two particles be connected in such a way that distance doesn't seem to matter? The truth is, no one fully understands it. That's what makes quantum entanglement so fascinating. It challenges our fundamental understanding of reality itself. In classical physics, the kind of physics that explains how planets orbit the sun, how cars move, and how we interact with the world, things are separate. If you move an object, it doesn't affect something else unless there's a force acting between them. But in the quantum world, everything is different. Entangled particles don't seem to obey those classical rules. One way to think about it is like a magical pair of dice. Imagine rolling two dice that are somehow linked together in a way that, no matter how far apart they are, they always land on the same number. Roll a 6 on one, and the other instantly shows a 6, even if it's on the other side of the galaxy. No message is being sent between them. They are just mysteriously connected in a way we can't fully explain. Even more strangely, the effect isn't caused by one particle influencing the other after the fact. It's not like one dice lands first and then forces the other to match. Instead, it's as if the two results were determined at the exact same moment, outside of time and space as we know them. This is what makes entanglement so unsettling. It hints at the possibility that reality is more deeply interconnected than we ever imagined. Some scientists think this might tell us something profound about the nature of space and time. Maybe, at the deepest level, everything in the universe is connected in a way we don't yet understand. Others speculate that entanglement could one day lead to revolutionary technology, like quantum computers that process information in ways classical computers never could, or ultra-secure communication systems that no hacker could ever break. In fact, quantum entanglement is already being used in real-world applications. Scientists are developing quantum encryption methods that take advantage of entanglement's unique properties to create unbreakable codes. If anyone tries to eavesdrop on an entangled communication channel, the very act of observing it will change the state of the particles, alerting the sender and receiver immediately. This could revolutionize cybersecurity, making online transactions, government communications, and even personal data completely secure. Beyond that, some researchers are exploring whether entanglement could help us develop futuristic technologies like quantum teleportation. While we're not talking about teleporting people like in science fiction, scientists have already demonstrated the ability to teleport information between entangled particles. This could one day lead to new ways of transferring data instantaneously, which would be a game changer for computing and communication. But despite all these advances, entanglement remains one of the greatest mysteries in physics. Even though we can observe it, test it, and use it in experiments, we still don't fully understand why it happens. Some theories suggest that entanglement is evidence that our universe isn't truly three-dimensional, but instead part of a deeper, more complex reality we can't directly perceive. Others propose that entanglement could play a role in understanding the fundamental nature of consciousness itself. The implications of entanglement stretch far beyond physics. It forces us to question the very nature of reality, time, and space. Could everything in the universe be connected in ways we haven't even begun to grasp? If two tiny particles can be linked across vast cosmic distances, what does that say about the universe as a whole? Could entanglement be a clue that everything, from the smallest atom to the largest galaxy, is part of a single, interconnected system? These are the kinds of questions that keep physicists awake at night. They remind us that despite all we've learned, the universe still holds secrets beyond our wildest imagination. Quantum entanglement is one of those secrets, a glimpse into a deeper reality that we're only beginning to understand. Whether it leads to groundbreaking new technologies or forces us to rethink our entire understanding of the cosmos, one thing is certain: entanglement is real, it's strange, and it's changing the way we see the universe. Quantum physics today, the dawn of a new reality. For centuries, humanity has tried to unravel the universe's deepest mysteries, but nothing has shaken our understanding of reality more than quantum physics. It's no longer just an abstract theory confined to chalkboards and equations. It's now the beating heart of our most advanced technologies. The quantum world, once dismissed as bizarre and paradoxical, is now the driving force behind innovations that are transforming the fabric of our lives. Look around. Every laser beam, every GPS signal guiding you home, every microchip inside your smartphone owes its existence to quantum mechanics. But this is just the beginning. The quantum revolution isn't just happening, it's accelerating. The world as we know it is about to change forever. At the forefront of this revolution are quantum computers, machines so powerful they could reduce today's supercomputers to mere calculators. Unlike classical computers that rely on bits, tiny switches that can be either 0 or 1, quantum computers use qubits. These qubits can exist in multiple states at once, thanks to a strange property called superposition. In essence, a quantum computer can perform countless calculations simultaneously, solving problems that would take traditional computers millions of years. And the consequences? Staggering. Imagine cracking the most complex codes in minutes, revolutionizing drug discovery, and simulating the vast intricacies of the universe with unprecedented precision. But there's also a darker side. Quantum computers could one day break modern encryption, rendering all online security obsolete. Every password, every bank transaction, every classified government document vulnerable in an instant. The world's greatest minds are now racing to develop quantum-proof encryption before it's too late. But quantum mechanics isn't just shaping technology, it's reshaping reality itself. Scientists are pushing the boundaries of what we thought possible, using quantum mechanics to explore concepts that sound like science fiction. Teleportation, for example, is no longer just a dream of Star Trek enthusiasts. Researchers have successfully teleported particles across vast distances using quantum entanglement, a phenomenon so bizarre that even Einstein called it spooky action at a distance. Two particles, no matter how far apart, can be instantaneously connected, as if communicating through an invisible cosmic thread. One day, this could lead to unbreakable communication networks, quantum internet, or even instantaneous data transfer across galaxies. And then there's time travel. Yes, you read that right. Some physicists believe that the strange behavior of quantum particles could hold the key to bending time itself. According to quantum mechanics, particles can move backward in time or exist in multiple timelines simultaneously. Could this mean time travel isn't just possible, but already happening at a microscopic level? Could our very notion of cause and effect be an illusion? These aren't just philosophical musings. They're questions that are forcing scientists to rethink everything we know about time and space. Perhaps the most mind-bending implication of quantum physics is its connection to consciousness. Some researchers suggest that the human mind itself might operate on quantum principles. Could it be that our thoughts, our choices, even our very existence, are entangled with the quantum fabric of the universe? Could quantum physics be the missing link between science and the mysteries of consciousness? Some believe that understanding quantum mechanics could finally answer the age-old question, what is reality? And then there's the biggest mystery of all, the universe itself. Quantum physics suggests that reality isn't fixed, but fluid, that particles don't have definite states until observed, that the very act of looking at something changes its nature. This has led some to an unsettling conclusion. The universe might not exist in a definite state unless it is being observed. Could this mean that consciousness is fundamental to reality? That the universe itself might be a giant quantum experiment? The implications of quantum physics are nothing short of revolutionary. We stand on the precipice of a new era, one where the impossible is becoming possible. Quantum mechanics is no longer just a field of study. It's the key to unlocking the deepest secrets of existence. What lies ahead is a future beyond imagination, where technology, reality, and even the nature of time itself could be rewritten. One thing is certain: the quantum revolution has begun, and there's no turning back. Quantum mechanics has completely transformed our understanding of reality, forcing us to abandon long-held assumptions about how the universe works. It has revealed a world that defies intuition, where particles can exist in two places at once, where the mere act of observation alters outcomes, and where the fundamental nature of existence is governed by probabilities rather than certainties. This branch of physics has not only reshaped science but also challenged philosophy, raising profound questions about the nature of reality itself. For centuries, classical physics provided a framework that made sense of the universe in a predictable and orderly manner. Newton's laws could explain everything from the motion of planets to the way objects fall to the ground. But as we peered deeper into the microscopic world, these familiar rules began to break down. The discovery of quantum mechanics in the early 20th century shattered the idea that the universe operates like a well-oiled machine. Instead, it revealed a chaotic, counterintuitive realm where the classical laws no longer apply. At the heart of quantum mechanics is the idea that reality is not as straightforward as it appears. Particles do not have fixed positions or velocities until they are measured. Instead, they exist in a state of superposition, where they can be in multiple places at once. The famous double-slit experiment demonstrated this bizarre phenomenon, showing that particles behave like both waves and particles depending on whether they are being observed. This led to one of the most puzzling implications of quantum mechanics, the observer effect, which suggests that consciousness itself might play a role in shaping reality. Another mind-bending concept is quantum entanglement, often described as spooky action at a distance. When two particles become entangled, their states remain linked no matter how far apart they are. A change in one particle instantaneously affects the other, even if they are light years apart. This phenomenon appears to violate the principles of relativity, which state that no information can travel faster than the speed of light. Yet, entanglement has been experimentally confirmed time and time again, leaving physicists searching for an explanation. Despite its strange and often paradoxical nature, quantum mechanics has led to some of the most groundbreaking technological advancements in history. It is the foundation of modern electronics, enabling the development of transistors, semiconductors, and computers. Without it, we wouldn't have lasers, GPS systems, or MRI machines. Even the internet relies on quantum principles to function. And now, as scientists push the boundaries of quantum computing, we stand on the brink of a new technological revolution that could change the world once again. But for all its successes, quantum mechanics remains incomplete. The biggest unresolved question is how it fits with general relativity, Einstein's theory of gravity. While quantum mechanics governs the microscopic world, general relativity describes the universe on a cosmic scale. Both theories are incredibly accurate within their own domains, yet they are fundamentally incompatible. Attempts to reconcile them have led to theories like quantum gravity and string theory, but so far, no definitive answer has been found. Then there is the question of what quantum mechanics truly means. The Copenhagen interpretation, proposed by Niels Bohr, suggests that particles exist in a superposition of states until they are observed, at which point they collapse into a definite state. But this raises a troubling question. What exactly constitutes an observer? Does it require a conscious mind, or is any interaction with the environment enough? Some physicists argue that the universe itself might be a kind of vast quantum system, with reality emerging from the act of observation. Other interpretations seek to avoid the problem of measurement altogether. The many worlds interpretation, for example, suggests that every possible outcome of a quantum event actually happens, but in separate, parallel universes. According to this view, every time you make a decision, an alternate version of you exists in a different universe where you made the opposite choice. This idea, while fascinating, raises more questions than it answers. If countless versions of reality exist, why do we perceive only one? There are also hidden variable theories, which propose that quantum mechanics is not truly random but rather governed by deeper, unseen forces. Einstein himself was a proponent of this idea, famously rejecting the idea of quantum randomness with his statement, "God does not play dice with the universe." However, experiments like Bell's theorem have largely ruled out the possibility of hidden variables, strengthening the argument that quantum mechanics is fundamentally probabilistic. And yet the mysteries continue to deepen. Quantum mechanics suggests that time itself may not be as rigid as we think. Some theories propose that the future can influence the past, an idea that challenges our very understanding of causality. Others suggest that quantum mechanics could explain the nature of consciousness, linking the workings of the brain to quantum processes. While these ideas remain speculative, they hint at a deeper connection between quantum physics and the fundamental nature of existence. As we explore these questions, new discoveries constantly reshape our understanding. The recent advancements in quantum computing, quantum teleportation, and quantum cryptography suggest that we are only scratching the surface of what is possible. Perhaps the next great breakthrough in physics will come from an unexpected direction, revealing a more complete picture of reality. But one thing is clear: quantum mechanics is not just a theory, it is a window into the deepest layers of the universe. It has shown us that reality is far stranger and more complex than we ever imagined. It has challenged our perceptions of space, time, and existence itself. And yet, for all our progress, we are still left with more questions than answers. Is quantum mechanics the final word on reality, or is it merely a stepping stone to an even deeper understanding of the universe? The truth is, we don't know. But that is the beauty of science. Each discovery opens new doors, revealing mysteries we never even considered. Quantum mechanics has revolutionized our world, and it will continue to do so. The journey to understand it is far from over. It may be just beginning. Subscribe now, and keep exploring the mysteries of the universe with us.